Welcome, curious minds, to another deep dive.
Yeah,
When we look around at our everyday world, things seem pretty straightforward, right?
absolutely. Bridges hold weight, water flows downhill, you throw a stone, it follows a path. Very predictable.
Exactly. Simple, stable rules. But then scientists started peering into the really, really tiny building blocks of matter.
And that's where things get weird. All that certainty, that predictability, well, it starts to unravel. They stumble into the quantum world.
A universe on the smallest scale that just defies common sense, doesn't it?
It really does. And our mission today is to give you a kind of shortcut through that initial descent into what must have felt like scientific madness. We want to pull out the key insights from the source material.
Yeah, so you can get a real handle on this huge scientific revolution. I think one of the founders put it perfectly, paraphrasing here, but something like everything we call real is made of things that can't themselves be regarded as real.
That's a mind bender right there. Because down there in the quantum realm, things can apparently be in two places at once. Fate seems ruled by chance.
And reality itself might only pop into existence when we look at it. It's wild.
Totally wild. And the most amazing part, this whole journey started with probably the last thing you'd expect.
Which was,
The humble light bulb.
no way, the light bulb. Okay, explain that. We're talking like late 19th century?
Exactly. Think Berlin around 1890, Germany's booming industrially, Edison's invention is the big thing.
Right, new companies springing up, wanting to make money off these electric lights.
Fortunes were being made lighting up cities. But they ran into a problem, a physics problem they didn't understand, lurking inside that simple bulb.
It was the mystery. They knew heating the filament made it glow, right?
Sure, they knew that. But they had no idea why the color of the light changed with temperature in the specific way it did. Seems basic, temperature and color, but the physics, a complete black box.
So the German government actually invested in figuring this out.
They did set up a big research institute, the PTR, in Berlin. And around 1900, they tasked Max Planck, a very methodical physicist, with cracking this deceptively simple problem.
So what was the core puzzle? Like with an old bike lamp?
Yeah, that's a good analogy. You pedal faster, right? More heat, brighter light.
And the color changes too. It goes from red to orange, yellow, but it never really gets deep blue, does it? Even if you pedal like mad.
Precisely. It gets brighter, maybe yellow-white, but not really blue or violet. Why not? That was the question.
So Planck needed better data.
Right. He and his team built something called a black body radiator, basically a perfect oven where they could precisely control the temperature and measure the exact colors, the frequencies of light coming off.
And what did they see?
Well, at around 840 degrees Celsius, it's orangey red. Crank it up to 2,000 degrees, much brighter, definitely whiter, but still surprisingly little blue light.
Wow. Even the sun, at 5,500 degrees, is mostly white light, not intensely blue or UV, considering how hot it is.
Exactly. This failure of things to get bluer and bluer, this lack of ultraviolet light at high temperatures, it was so baffling, so contrary to the physics they knew.
They called it the ultraviolet catastrophe. Sounds dramatic.
It was a catastrophe for their theories. Planck's first big step, though, was finding a precise mathematical formula. It perfectly linked the light's color, its frequency, to its energy. He didn't fully understand why it worked yet, but the math fit the data perfectly.
Okay, so one mystery brewing. But there was another one popping up around the same time, wasn't there? Something about light and electricity.
Yes, another weird anomaly that really put the cat amongst the pigeons. Scientists studying radio waves noticed that if you shone a bright light on metal spheres, sparks jumped between them more easily. Light was somehow affecting electricity.
How do they investigate that more closely?
With a device called a gold leaf electroscope, you charge it up, maybe give it extra electrons, and two little gold leaves inside push apart because they repel each other.
Got it. So what happens when you shine light on it?
Well, here's the kicker. Shine intense red light on the metal plate connected to the leaves. Nothing. The leaves stay apart. Doesn't matter how bright the red light is. But then shine even a dim blue light, especially one rich in ultraviolet. Bang! The leaves collapse instantly.
Whoa. So the UV light was knocking the electrons off the metal, getting rid of the charge.
Exactly. But why was UV light so good at it and red light totally useless, even if the red light was much, much brighter? This was the photoelectric effect.
Okay, so we have the ultraviolet catastrophe, hot things not making enough blue light, and the photoelectric effect, blue UV light knocking out electrons when red light can't.
Yeah.
And the existing theory couldn't explain either.
Not at all. Both flew in the face of the accepted wisdom, which is that light is purely a wave.
And the wave theory works so well for other things, like shadows aren't perfectly sharp, right? They have fuzzy edges because light waves bend around corners.
Or soap bubbles. Those beautiful swirling colors are perfectly explained by light waves interfering with each other. Light as a wave, ripples of energy spreading out that made perfect sense. It was, common sense physics.
But for these new problems,
For these new problems, the wave theory just started coming off the wheels. It couldn't cope.
can you give us that water wave analogy again to show why it failed?
Sure. Think about waves in, say, a big water tank. Small, gentle waves might lap against something but not do much. They don't have much energy.
Right.
But big, powerful waves, they can knock things over easily. More intensity, more energy, more impact. That's how waves work.
So if light is a wave, a brighter light, a more intense wave should have more energy.
Yeah.
It should be better at knocking electrons out.
It absolutely should. But the experiments showed the opposite. No matter how intense the red light wave, nothing. But even a weak little UV wave could do the job instantly. Thinking of light as just a wave, well, it just wasn't adding up.
This sounds like a real crisis point for physics. Who broke the deadlock?
Well, along comes Albert Einstein in 1905. He was already making waves, pardon the pun, with relativity, but this was something else entirely. He proposed a truly radical, almost heretical idea to explain the photoelectric effect.
Which was?
He basically said, forget light being a wave just for this problem. Think of it instead as a stream of tiny, discrete, bullet-like particles, packets of energy.
Particles, not waves.
Particles. He called each particle of light a quantum. The idea that light could be a particle seemed, well, frankly, crazy to most physicists at the time.
But did it work? Did it explain the photoelectric effect? Let's use that ball analogy.
It explained it perfectly. Imagine trying to knock over tin cans, those are the electrons. If you throw lots of light, low-energy red ping-pong balls at them...
Nothing happens. They just bounce off.
Right. That's like intense red light, lots of quanta, but each one has too little energy because red light has a low frequency. They can't knock an electron out.
Okay, but now use heavier, high-energy blue golf balls.
Uh-huh. Now, even just a few of those blue golf balls have enough energy individually to knock a can over easily.
And that's like the ultraviolet light. Each UV quantum carries more energy because UV has a higher frequency. So even a dim UV light, just a few quanta, can knock electrons out.
Exactly. It elegantly solved the photoelectric puzzle. Each light particle, or quantum, had an energy linked directly to its frequency, its color.
And you mentioned it also solved the ultraviolet catastrophe, the light bulb problem.
It did, because creating a high-energy UV quantum, one of those blue golf balls, takes significantly more energy than creating a low-energy red one. About 100 times more, in fact.
Ah, so that's why hot things struggle to make much UV light. It's just too energetically expensive to make those high-energy quanta.
Precisely. So Einstein's quantum idea, thinking of light as particles, it solved both mysteries at a single stroke. It was revolutionary.
This really feels like the birth of something entirely new.
It absolutely was. This moment really signaled that classical physics wasn't the whole story. We needed a completely new approach. This is where modern physics, quantum physics, truly began.
But it left physicists with a massive headache, didn't it? A paradox.
Oh, a huge one. Because light was definitely a wave thing, shadows, soap bubbles. But now it was also definitely a particle thing, photoelectric effect, UV catastrophe. How could it be both?
That's confusing enough. But the weirdness didn't stop with light, did it?
Not by a long shot. This wave-particle duality, as they called it, was just the opening skirmish. The real battle for the nature of reality itself was about to begin.
You mentioned the 1920s earlier, a time of huge cultural shifts. Jazz, new art, new politics.
Yeah, and the upheaval in physics during that decade arguably eclipsed them all. It went deeper than just light behaving strangely.
Because the same weirdness started showing up with matter itself, with electrons.
Exactly. Remember, electrons were thought to be straightforward, tiny solid particles like miniature billiard balls. That was the standard picture.
Until an experiment in the mid-1920s at Bell Labs.
That's the one. They decided to fire a beam of electrons through a thin crystal. The regular atomic structure of the crystal acted like a screen with many, many tiny slits, effectively like two slits very close together.
Okay, so electrons, little particles, going through slits. What did they expect to see on the detector screen behind it? Maybe just two bright patches where the electrons hit.
That's what you'd expect for particles, but remember the water waves going through two gaps.
Right, they create that interference pattern, bands of bright and dark where the waves add up or cancel out. It's the classic signature of a wave.
Well, guess what they saw when they fired electrons, supposedly particles, through the crystal slits?
Don't tell me.
Exactly the same kind of pattern, alternating bands. An interference pattern. Electrons were behaving like waves.
Wait, first light acts like particles, now particles act like waves. What is going on?
It gets even weirder. They refined the experiment later to fire electrons, one single dot electron at a time.
Okay, one particle at a time. So it can't interfere with other electrons.
Wow.
What happens then? Does it just hit randomly?
Each individual electron does seem to land at a random spot. But, and this is the mind-blowing part, as you fire more and more single electrons, the pattern they build up collectively is that same wave interference pattern.
How? How can one single electron going through the slits by itself contribute to a wave pattern? A wave needs to go through both slits at once to interfere with itself.
That's the profound mystery. It suggests that each individual electron, somehow, knows about both slits, behaves like a wave spread out across both paths, even though it's detected as a particle at only one point on the screen.
My head hurts. Who tried to explain this?
This is where Niels Bohr and his colleagues stepped in. They developed the mathematical framework of quantum mechanics, a theory that, frankly, embraced the contradictions. It worked incredibly well for predictions, but it was almost impossible to visualize or understand intuitively.
Bohr had that famous quote, right?
He did. Anyone who isn't shocked by quantum theory hasn't understood it. And he meant it.
So what was Bohr's explanation for the single electron creating an interference pattern?
He argued that you can't actually talk about the electron as a physical object with a definite path while it's traveling. All quantum mechanics can tell you is the probability, the chances of where you might find it.
So it's like a wave of probability.
Exactly, a wave of chance. This wave does travel through both slits, just like a water wave, and it interferes with itself. Then, when this wave of possibility hits the detector screen, poof, it collapses. And the electron appears, seemingly randomly, at one specific point, but the probability of it appearing is highest where the wave interfered constructively.
Okay, let me try the spinning coin analogy again. While it's spinning, it's neither heads nor tails, just a blur of both possibilities.
Right. It's in a superposition of states, you could say. Only when you stop it, when you measure it, does it become definitely heads or definitely tails.
So Bohr was saying the electron is like that spinning coin. Its wave of chance goes through both slits simultaneously. It's taking both paths. And only when it hits the screen, when it's measured, does it land as a particle in one place.
That's the essence of the Copenhagen interpretation, which Bohr championed. The act of measurement forces the quantum system to choose a definite state from its cloud of possibilities.
Which implies
What?
that the electron wasn't really anywhere specific before we measured it. It was just a set of possibilities.
That's the staggering implication. Bohr suggested you can never know where the electron actually is until you measure it. It's not just that we don't know, it's that the position itself isn't fully real until observed. It's like the act of looking conjures its reality into existence.
Wow. Okay, I can see why Einstein hated that.
Hated it with a passion. He famously quipped, "Does the moon cease to exist when I don't look at it?" He couldn't accept that reality was fundamentally fuzzy or dependent on observation. He believed there had to be some deeper, hidden reality.
And he thought he found a flaw in Bohr's idea using something called entanglement.
Yes, working with Rosen and Podolsky, Einstein devised a thought experiment involving entanglement. It's this strange connection between two quantum particles, like two electrons, that might be created together. Their fates remain linked, no matter how far apart they travel.
So like our spinning coins again, but now we have a pair created together.
Exactly. According to Bohr's Copenhagen view, neither coin is heads or tails until you look. But because they're entangled, the instant you measure the first coin and it becomes, say, heads,
The other one, even if it's light years away, instantly becomes tails.
simultaneously. The outcomes are random individually, but they're always perfectly correlated, always opposite in this case.
And Einstein said this was spooky action at a distance because it looked like faster than light communication.
Precisely. It seemed to violate his own theory of relativity. He thought this proved Bohr's interpretation must be wrong, or at least incomplete.
So what was Einstein's alternative? How did he explain the correlation without spooky action?
He proposed what's called hidden variables. He argued the particles were more like a pair of gloves put into separate boxes. One is left, one is right, determined from the start, but hidden from us.
Ah, So when you open one box and find the right glove, you instantly know the other box has the left glove.
Right. But crucially, finding the right glove doesn't change the other glove. It was always left. Your knowledge changes instantly, but there's no spooky physical influence traveling between the boxes.
Okay, so the big question was, is the quantum world like Bohr's magically linked coins, where properties are created on the fly by measurement? Or is it like Einstein's gloves, where properties are fixed from the start, just hidden?
That was the deadlock. Bohr's spooky coins versus Einstein's hidden gloves. And by the late 1930s, with war looming, the debate kind of stalled.
Then after the war, science shifted gears, right?
Yeah.
More practical applications.
Very much so, especially in America. Quantum mechanics was just incredible.